We want to calculate the flux integral, which is a double integral over the surface S of f dot differential S, where the vector field f is given here, and the surface S is the surface of the box bounded by these three planes and the coordinate planes. So let's first look at this graphically. The surface S is bounded by these 6 light blue planes, and the vector field f is graphed in gray. So the value of the flux integral will give us the net flow across the 6 surfaces of the bounded box. And we'll evaluate the flux integral using the divergence theorem. So before we set this up for review, the divergence theorem states the total divergence of a vector field in a solid region V equals the total flow across the boundary surface S. So the region V must be a solid region bounded by S, oriented by a unit normal vector directed outward, and the partial derivatives must be continuous over the region V. So under these conditions, the flux integral is equal to the triple integral over the region V of the divergence of the vector field f differential V, which can also be written in this form here. So this shows the relationship between a triple integral over a solid region and a surface integral over a surface. This is a 3D version of the flux form of Green's theorem. So going back to our example, looking at our formula below, and the vector field f, p equals e times sine y, q equals e to the x cosine y, and r equals yz squared. So let's go ahead and find our partial derivatives. So the partial derivative of p with respect to x is equal to the derivative of e to the x sine y with respect to x, which should be e to the x sine y. And the partial derivative of q with respect to y is equal to the derivative of e to the x cosine y with respect to y, which would be e to the x times negative sine y, or negative e to the x sine y. And the partial of r with respect to z is equal to the derivative of yz squared with respect to z, which would be 2yz. So the flux integral, or the given surface integral, is equal to the triple integral over the solid region V of the sum of these partial derivatives, which should be e to the x sine y plus negative e to the x sine y, or minus e to the x sine y, plus 2yz. And then for differential v, let's go ahead and use the order of integration given by dx, dy, dz. The limit integration for x will be from 0 to 4. The limit integration for y will be from 0 to 5. And limit integration for z will be from 0 to 1. Let's go ahead and evaluate this on the next slide. We'll notice how this difference will be 0, so this simplifies to the triple integral of just 2yz. Again, we have dx, dy, dz. So we first integrate with respect to x, treating y and z as constants. So the antiderivative would just be 2yz times x, or 2xyz. Performing substitution for x, we would just have 2 times 4 times yz, and then when x is 0, it's just 0. So we have the double integral of 8yz dy dz. And now we integrate with respect to y, treating z as a constant. So we'd have 8z times y squared divided by 2, which would be 4y squared z. And now substituting for y, when y is 5, we have 4 times 5 squared times z, minus when y is 0, we have 0. So we have the integral from 0 to 1 of, this is going to be 25 times 4, that's 100z. And now we integrate with respect to z, so we have an antiderivative of 100 times z squared divided by 2, which would be 50z squared. Evaluating here, we just have 50 times the quantity 1 squared minus 0 squared, which is just equal to 50 times 1, or 50. So the value of the given surface integral, or the flux integral, is equal to 50. And this value represents the total flow across the boundary surface S of the region, as well as the total divergence of the vector field in the solid region V. I hope you found this helpful.